Welcome back, welcome back, welcome back to Physical Science. This is Miss Lisa. I'm looking in the camera. It's a YouTube channel where I teach science and math, and this is physical science, primarily to homeschoolers, but if you just like the way I explain things, you are welcome to watch. Welcome, welcome, welcome. I am glad you are here. I would like you to like, share, and subscribe. I know every YouTuber says that, but I have this goal that I can get 1,000 subscribers, and then I don't have to record the video and then upload the video and take that time. I can just do YouTube Live, which is like Facebook Live, and I could do them one after another, and it would save time. So I'm lazy and I'm busy, and I don't like the time having to upload the videos. I want them to go straight the way they do with Facebook Live. I used to do my classes on Facebook Live, but Facebook is a pain, and you can do a whole lot more with YouTube. I can put it into playlist, and it will be there forever. Facebook tends to take things away after a while, so I'm switching to YouTube, and I don't like it that they don't let me live stream. I want to live stream, but they say my channel is too small, that I have to have 1,000 subscribers to be allowed to do that. So I have a goal. My kids say, "Mom, it's not going to happen." I'm like, I'm already at 250. Surely there's 750 more homeschoolers out there who want to take math and science at a high school level free. And also, if you don't know, there is a Facebook group that goes with this that will have tests and answers for the parents. So you can have your high school class right here. So I'm Miss Lisa, and we are talking, and we have 2 books for this class. I told you that shocking news last time, what I did with it. This book is what I've been using for this class for a very long time, and it's very good, but it's an older book, and to make this class a little bit more flexible, I guess is the best word, we're using 2 books. They're both older books, so you can get them for cheap off of eBay and places like that. And this one is our primary textbook. It's a newer book, and it's a little bit more advanced, so it's more of a mid-high school level book, where this one can do good for 8th grade, 9th grade. It's more of a lower high school level, but I've had many a senior take this class and get high school credit for it. So just know that with having the 2 books, that if you're a little bit younger, you might want this to be your primary book, and read it first, because the reading level is just a little bit lower in this book. It's a little higher in the other book. They cover the same stuff. The book that I'm using for the primary book is just a little bit higher reading level, a little bit more detailed. It prepares you a little bit better for physics. It's a little bit more advanced. So if that book's too much for you, find the topic that I talk about in this book and read this book instead. But we're hanging on to this book too. Not only is it the simpler reading level, but it also has really good labs with everyday material. So we're going to be using primarily this one for our lab book and the other one for our textbook. But they cover the same topics. It's pretty much the same thing. But I just wanted to use the newer edition of this book to be our primary text, this one. So today we are talking about chapter 2, and we're going to be describing, let me make sure I'm at the right place. Yes, I am. We're going to be talking about motion. So physical science, is a mixture of chemistry and physics, and this book does the physics first, and the other book kind of jumps around. So we'll be jumping around that other book to be able to pick up the labs. But you can do it either way, but we're just going to do physics first because that's the way it is in this book. So, describing motion. Y'all know what motion is. It's when something changes position. And one of the things that you need to keep in mind when you talk about motion in physics is a frame of reference. Have you ever been sitting on a bus, or maybe in a big minivan, or what are they called? The conversion vans, the real big ones. And something next to you starts moving forward, but suddenly you kind of jerk because you feel like you're rolling back, but really it's the other one going forward. So your frame of reference that was telling your brain that you were still moved, and it made you think you were moving when you weren't. So frame of reference is one of the things to think about with motion. Like, say you are riding in a car and you look down and it looks like, and you took your physical science book because you love it and you took it with you, and you look down at your lap and it appears that it is still. But if someone was outside the van and they looked, they would know your book is moving down the road that's moving. And right now it appears that I am sitting still in a room in my house. But isn't the earth turning? About 300 miles an hour, I think. And then isn't the earth going around the sun? And isn't the sun going around the galaxy? And isn't the galaxy going around the universe? We are zipping along. But for our frame of reference in physics, we are going to pretend like none of that other stuff is going on. And we would say that I am sitting still in a room. We're not going to think about the fact that the earth is turning. Too many variables. We have to limit it. All right, so the next thing is distance. Distance is, how many meters or how many feet are between 2 points. Distance is always positive, and in algebra and in geometry, you learn the distance formula. If you have a TI-84 graphic calculator, I can give you a distance program that you can figure it out. And then what I mean when saying that distance is always positive is that I say it's 2 miles from my house to the library. And I also say it's 2 miles from the library back to my house. It is not negative 2 miles from the library to my house. So we always state distances as positive. Now, displacement is a little bit different. With displacement, you do think about it in terms of positive and negative, because like say we've got this marker, we could say that it went this way and was displaced, and then it went back to where it started, so its total displacement was 0. So or it goes over this way. If this way is positive, that way is negative, then you can say it goes in a negative direction. So displacement can have positive and negative. And you have a nice little illustration in your book on page 39 of someone running around, I think it is a football field, and seeing that. All right, our next thing we're going to talk about is speed. Speed, I wrote down a little board for you, is distance over time. And you're familiar with this. If your mom is, driving, or you, if you're older, driving down the highway and the speed limit is 55 miles an hour and you are going 70 miles per hour, then you can get a ticket. So the speed is the distance divided by time, like miles divided by hours. When I very first started teaching, decades ago, and we won't talk about how many, I had some students, and I said, how can we remember this? Speed is distance over time. What is something that we could think of as a class, as a mnemonic device to remember this formula that's going to be on the test? And I had this one kid on the front row look at me, which is the most dead eyes, and he said, dead science teacher. And I thought, oh no, this is going to be harder than I thought. He didn't kill me though, and I didn't kill him, so it all worked out. He wasn't around long. That kid, he said, dead science teacher. He dropped out of school, I think, real quick after that. He was just not happy. School was not where he wanted to be, and learning science was not what he wanted to be doing. So let's look at how you do a speed equals distance over time, or any problem in physics and math if it's a formula problem. What I want you to do first is I want you to list your knowns and unknowns. So my known in this problem, my distance is 750 meters. My time is 25 seconds. And what I want to know is the speed. So I want you to make a little list over to the right-hand side of what you're given in the problem and what you're looking for. In physics, and that's what we're doing, our problems are word problems. And what makes them hard is not the math, it's the words. So we want to get rid of all the words and get it just to the math. The math is the easy part because we can do it on our calculator. So we're going to list our numbers, our knowns and unknowns. Next, you think, is there a formula that relates distance, time, and speed? And we say yes. Speed equals distance over time. So the next thing I want you to do is to write your formula. And every single time, on every problem, I want you to write your formula. That will make you memorize it. And always write it in the famous way, like E equals mc squared is the famous way for that formula. Speed is distance over time is that famous formula. Write it the famous way. Do not rearrange it. Some books want you to rearrange formulas. Don't do it. Just don't do it, because one day you'll be old like me, and you will know your formulas. You will memorize them if you write them every time on every problem the same way. I know hundreds of formulas because I teach math and science, all different classes, and I literally have memorized hundreds of formulas, and it's very convenient that I don't have to go, what was that formula about speed? I need to look it up. Nope, it's here. It's in my brain. So then after you have your formula, then you sing a song. You're going to sing Substitute. It's by The Who. It's before my time and yours. And it's the song we sing. It just helps us remember what we're going to do next if we sing little songs and do little dances. Then where the D is, I'm going to write 750 meters. And where the T is, I write 25 seconds. You write the units too, because we do the math to the units too. Like miles per hour means miles divided by hours. So we want to get the right units, and we do that by doing the math to the units. So then on our calculator, you need a scientific calculator for this class, you do 750 divided by 25, and it's 30. And then meters divided by seconds is meters per second. Now, whenever you draw a fraction in here, I want your fraction bar, the little line that goes on the fraction, to be flat. I don't want you to do a slash like I did over here in the units. Only if it's the units do I want you to do a slash. Why is that? Because y'all write terrible. And you'll start with it being 1/2, and in a minute it will be 112. I've seen it over and over again. See, 1/2, you see that? And then they'll end up then they miss the problem, because they forgot that was 1/2, and they'll turn it into 112. I've seen it over and over again. So make your fraction bars not slash like this, only if it's a unit. And then you write the answer with the unit. In science, a number without a unit is meaningless. We have no idea what it is. It has to have a unit. And often teachers will take off half for the unit. If you didn't get the unit, then half credit gone. So you could have 100 on a test and get everyone right, and you're only going to make an F, a 50, if you forgot the units. So don't forget your units. Okay. The next thing is you can graph these speeds, and here's an example. You would do distance on this side and time on the bottom. This is called the dependent and independent variable, and the time is the independent variable. You can't change time. Time is what it is. So the thing that you can't change, you write on the x-axis across the bottom, and the thing that's being experimented on, the thing you can change, goes on the y-axis or on the side. And then you graph it. You make points and graph it. If you don't know how to make a graph, I've got some videos in my math classes where you can see that, how to make a graph. I think Algebra 1 has some graphing videos already you can find. But I'm sure there's other videos out there on how to do a graph. If we graphed distance speed, the one that's flatter is slower. So these are two different speeds, and the steeper line would be a faster. So this is me running, and that's my child Joshua running. I run like 30 miles at least twice a week, and that's me running slow, and that's Joshua running really fast. I'm the slow line, but I'm still going. There you go. All right, so go back to your book, and so displacement would have a direction to it. It's not just a distance, it's a distance in a direction. Speed is distance over time, and you can see where they did the problem there. Also, they showed how you can have constant speed or changing speed. And when I first started teaching, I had gotten at KB Toys, which has been out of business forever. But I bought for $4 this little truck, and it was one of those monster trucks or jacked up trucks where, you know, it's got tires and the way up high, it's got the bottom, this little toy truck, and you put a little battery in it and turn a little switch on the bottom, and it was constant speed. And we would do the lab that is in the physical science lab book with that little truck, and it was great. It would just do it. We would graph it. It was beautiful. And then one of those bad children that I taught stole my truck. And for years, I have been looking for a new constant speed truck that's not pull back and go because it gets faster. That's acceleration, not constant speed. And not one that veers off and bounces off walls and flips over. All of them are just terrible. Finally, last year when I taught this class, there is a fly in here. When I taught this class last year, one of my students brought his RC, his remote control car, and it did pretty good, but it did accelerate a little bit. It wasn't as good as the $4 little truck I had. Now I'm back teaching public school, and I have seen the physics stock room, and my department head has some constant speed cars in there. And I was like, oh, those are great. They're constant speed. She's like, yeah, the kids love them. And I'm like, you don't know how hard those are to get. And it's because they sell things. There are science supply companies that will sell to public schools that do not sell to homeschoolers. And like, it's just how it is. The old places I used to buy from when I taught public school, they don't sell to homeschoolers. So we need home training tools. Our science supplier for homeschoolers have a really good constant speed car for cheap. I want it for $4 again. So anyway, if you got one, you'll be able to do the lab. That's the constant speed lab, and I'll assign it. But if you don't have one, sorry, I feel your pain, because I personally don't have a good constant speed car either. So a constant speed car just goes at one speed. It doesn't speed up, it doesn't slow down. You just flip the switch and off it goes. And it makes a very straight line for your distance versus time line. Then the next thing in your book talks about is changing speed, and there's a graph of this. The car goes fast, it slows down, it stops at the red light, it goes around a curve, and that's what the graph looks like. You'll see in your book, it goes up and down. It's not just the straight line. Now, average speed, like a lot of times we know average speed, like say your speed is to your grandma's house is usually, you average it out. You take the miles to grandma's house and you divide it by the time it took you to get there. And you can say that your average speed to your grandma's house was 40 miles per hour. Now, were you going 40 miles per hour every second of that trip? Oh, no. You had to stop at red lights and you had to stop at stop signs. And then sometimes you were going faster than 40 and sometimes you were stopped. But you can get your average speed by taking your total distance divided by your total time. The other thing is instantaneous speed, and that would be if on the way to grandma's house, the policeman sees you zipping along and he thinks you might be speeding, and he fires his radar gun at you, not his real gun, his radar gun, and he clocks you and he goes, oh, you're going 35, and it's a 35 mile an hour speed zone, you're good. That's your instantaneous speed, your speed at that moment. And they make those now that you can use like with Hot Wheels and stuff. They have little instantaneous speed things you can do, which is really cool. My boys have always wanted one and have never gotten one because they're a little bit pricey, but they're very cool. That just regular old people, you don't have to be a policeman now to have one of those where you can find out something's instantaneous speed. It's very fun. All right, so we already talked about graphing motion. I showed you that. And look in your book and you can see how the graph would change. Now, what is the difference in speed and velocity? Speed is distance over time. Velocity is speed plus direction. So if I tell you I'm going 55 miles an hour, that's my speed. If I tell you I'm going 55 miles an hour northeast, that's my velocity. Now, this is it's one of my pet peeves. I have many, but this is one of my pet peeves. In physics books, it will be a speed. They will give you a distance and a time, and what they want is speed. They do not give you a direction, but they will say, what is the velocity? And the reason why they're saying it is because it sounds more sciencey, and they're nerds. They're just nerds, and they want to use the sciencey word, even though it's wrong. Drives me crazy. I was tutoring this one girl named Greer a few years ago, and she'd say, what's the velocity? And I'd say, we can't do the velocity. We don't know the direction. All I can tell you is the speed, and this is the speed. It's not a velocity. And she's like, Miss Blackburn, I just have to get the right answer. I just need the answers. my teacher is calling it a velocity, so we're just going to call it a velocity, okay? I was like, okay. I won't be so picky about it. But a velocity has a direction, a speed does not. All right. It talks about in your book about how the earth moves, the earth's crust moves, and that's what causes earthquakes. We had one here not too long ago. I'm in Georgia and we don't ever have earthquakes, but there was one in Tennessee, and all these people on Facebook felt it here right where I live, and I had no idea there was an earthquake. One time there was one here many years ago when my child, who's a freshman in college, was he was about 4 or 5, and I was sitting at the kitchen and I hear boom boom boom, and I thought my son Joshua had fallen down the stairs. I'm like, Joshua, are you okay? And he's like, sure. Why do you think something's wrong? So it made a boom 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 noise. I don't know why, but it was a little bitty earthquake that you could feel here. I mean, and then of course people put on Facebook, they made their porch furniture fall over and say, we survived the earthquake of whatever year it was, because it was really nothing. All right, so what is acceleration? It's the next topic in your book. And acceleration is speeding up. You knew that, right? Slowing down, that's a negative acceleration. So slowing down is actually, in physics, a changing direction, is acceleration. It's just a negative acceleration. Or, and this is the hard one, changing direction. If you have constant speed, but you're going around a curve, that is actually considered an acceleration in physics. Y'all are probably too young to drive, but if you're old enough to drive, think about this. When you are speeding up, you give it more gas. To slow down, you press the brake. If you want your speed to remain constant as you go around a curve, you actually have to give it more gas. So your car knows that it's an acceleration, even though you don't. It takes more energy to go around that curve than it does to go straight. So acceleration in physics is speeding up, slowing down, or changing directions. I know it's weird, but it's what it is. All right. Your book says and changing directions. To calculate acceleration. So acceleration is, more fun with sound effects, is this formula. It is acceleration is your final velocity minus your initial velocity over time. And if they only give you a speed, it's your final speed minus your initial speed over time. They're just trying to be fancy. It is, and you can think about this, in science and math, a triangle is the Greek letter delta, and it means change or difference in. So it's delta V, meaning it's the change in speed or velocity divided by time. By tradition, this acceleration is written in cursive, and so is the V for velocity. It's written straight down and then curved up on the other side. You go doop, doop. But so a lot of times you see it in italics. So here's an example. We were going to find out the acceleration. We started off at 0, and then we ended up at 80 meters per second. And it took us 20 seconds was how long our experiment went. So it's final minus initial, because initial is usually 0, and we don't want to make it negative when it's not. It's the change in acceleration. So we say 80 minus 0 divided by 20, and that is 4, and the units is meters per second squared. Now, this math is going to be too hard for some of you that I'm about to say, and if it is, just ignore it. How do we do the units on the math? How did it end up, the math on the units? How did it end up being meters per second squared? And this is how. There is a rule in math that if something is in the denominator of the denominator, it gets to move up to the numerator. I can show you why mathematically it has to do with, to divide is to invert and multiply, but I call it the Jesus rule of math, because Jesus said that the first will be last and the last will be first. And I feel like if I was a number, I would feel like I was in the last if I was in the denominator of the denominator, and then I would get to move up to the numerator, which seems to be like the prime location if you're a number. I don't know if that's true, but it just seems that way. So see how that is a numerator, a denominator, and another denominator. So this gets to move up, and it makes it meters per second squared. That I'm oversimplifying, but just know there's a mathematical reason why behind that unit. Okay, that'll do for now. The next thing, okay, so we did is calculating acceleration. You can see it in your book. And so acceleration can be positive or negative. Slowing down is negative acceleration. Then it talks about amusement park acceleration. And we in the Atlanta area live near Six Flags, and they actually do a physics field trip in the spring. They have it where you can go on a field trip to Six Flags. It costs, but you can go. And they have physics guides where you can go do your physics, your physical science at Six Flags, and it's really cool. So, you know, if you got a chance, you can do it. They also have a great homeschool day. It's in the spring. It's just for homeschoolers. But they changed it year before last where they let the homeschoolers go in with the education day, and they made the homeschool day a whitewater, which I love whitewater, but I really liked that homeschool day at Six Flags. But anyway, they have them, I think, at Disney and some of those other places. So, you know, take full advantage of all your homeschooler things. Okay, so the last thing is motion and forces, and for this chapter, and it's just an introduction to it. Our next chapters are going to be all about forces, but we're going to go ahead and define what is a force. A force is simply a push or a pull. It is something that pushes something or pulls it. So I can push on this wall, I'm exerting a force. Okay, now no work is done unless I can move the wall, but just to push on it means I'm exerting a force on it. And forces can cause motion to change. If I push on a car, it can roll. And like a toy car. But one time, my family owns a 1978 VW bus. And when we very first bought it, it wouldn't go into reverse. And so we had pulled into a parking place and we were like, oh no, what are we going to do? Well, my husband and all my kids were in it, and I got out and I pushed the bus all by myself. They're really light, so don't be overly impressed. But my little kids were, they were like, wow, Mom's a superhero. She just pushed the bus with all of us in it. It was pretty easy, but I felt pretty powerful. So when you push something and it moves, then I pushed it, so that caused unbalanced forces and it moved. If something is still, then it has balance forces. Like right now on the table in front of me is this glass of water. And the gravity is pulling on it. That's one force. But the gravity's pulling it down, but the table that it's sitting on is holding it up. So the glass is neither heading to the earth by gravity or floating up into the sky. The forces on that glass of water are balanced, so it is said to have a zero net force, which means it's not going anywhere. If there are unbalanced forces, like say I shove it forward, then there would be more force from my hand. It would become unbalanced, and I would push it forward, and then gravity would pull on it, and it would probably break because it's a glass. It is up, and this floor is wood. So reading your book about balanced and unbalanced forces and how that causes motion. Now, what is inertia? Inertia is the tendency of an object to resist change. And it goes, you can hear it in Newton's first law of motion. There was a guy named Sir Isaac Newton. He was brilliant. He figured out about gravity. He made up calculus, and he has the three laws of motion. There's like nobody like him. He's an amazing, amazing, brilliant mind. And he did it like during quarantine, during the plague. So like I've been in quarantine with COVID, and I have not invented anything great. I've just made a bunch of YouTube videos for you guys. But he invented calculus during that time. So anyway, his first law of motion is this. An object in motion tends to stay in motion. An object at rest tends to stay at rest unless an outside force acts upon it. What that means is you're wearing ice skates. I know it's hard for us in Georgia to imagine, but try to imagine. And you're sliding across the pond. You have a push to get you started, but you will keep going and going and going, and probably till you hit the wall on the other side or a tree or something. You're going to keep going until something stops you. Now, you would go forever if it wasn't for friction. Friction is a force that will eventually slow you down and stop you. But if there is no friction, you would just keep going forever. You throw a ball, it would go forever. It's just like in outer space if there's no friction. And then an object at rest tends to stay at rest. If something is sitting still, then it doesn't just get up on its own and start moving. It will only do it if an outside force acts upon it. So an object in motion tends to stay in motion. An object at rest tends to stay at rest unless an outside force acts upon it. That is the first law of motion, and it's inertia, that things that are going keep going, and things that are stopped stay stopped. They resist change, and that's what inertia is. Now, we use inertia in common everyday speech, which you can understand. Imagine that this great big football player is running at you and doesn't see you, and you don't have time to get out of the way. He tries to stop as he sees you at the last minute, but can he? No. You're going to get flattened because he's got too much inertia, too much momentum, but he's going to keep going. He cannot quickly and easily stop. He's got too much inertia, too much tendency to keep going because he's going. And unless an outside force acts upon him and gets him to stop. Like with your car, it could be brakes. So your book talks about crashes, what happens, and safety seat belts, how they help stop you from continuing forward with that inertia and going through the windshield. So you need to wear them. Now, I will put in the comments the homework, what I want you to do, what I want you to read, and what labs I want you to do. And come back next week and we'll learn more physical science. Math and science are great, but right now science is great. See ya soon.